Assalamualaikum. Hi everyone. We are now into section 4.4.3 and the title is Variation of Parameters. Before this, we have learned the superposition approach. Do you remember what is this used for? The superposition approach is used to find the particular solution for a non-homogeneous linear differential equation with constant coefficients. So to apply this superposition approach, two conditions must be met. Firstly, the coefficients in the equation must all be constants. And secondly, the gx must belong to only one of this group of functions. The gx can be a constant, the gx can be a polynomial, or an exponential function, or a sine or cosine function. Or the GS can be any finite sums or products of functions in this group. So these two criteria must be met in order for us to be able to use the superposition approach. If one of these conditions is not met or both are not met, then we cannot apply the superposition approach. The question is, what if we encounter a problem which is non-homogeneous and it is linear, but the coefficients are not constants? And what if the gx does not belong to one of this group of functions? So how do we solve such type of problem? Okay, so to solve the problem, we have a method that is known as the method of variation of parameters. Before I introduce you this method, let us firstly look at equation number 20. Equation number 20 is an nth order non-homogeneous linear differential equation. Take note of the coefficients. The coefficients are written as a function of x. a0 of x, a1 of x, a2 of x, a sub n of x. These coefficients are written as function of x, meaning that they may be constants and they may also be variables. Okay, so if the coefficients are variables, then we cannot use the superposition approach. We can use the method of variation of parameters. So there's no restriction on the application of the method of variation of parameters. The method of variation of parameters can be used whether for the differential equation for if the coefficients are constants, or they can also be variables. And secondly, there's another thing that we can take note of is that the GS can be any function. The GS does not have to belong to a certain type of functions only. It can be any function. The GS can be a logarithmic function, it can be a reciprocal function such as this 4 over x, or it can be a tangent function, or it can be an inverse trigonometric function, or it can be a secant function, etc. So it doesn't have to be only a constant or polynomial or exponential or sine or cosine. So the GS can be any of these type of functions. It can be any functions. So that's the advantage of using the method of variation of parameters, because it has no restriction on what the coefficients have to be, and it has no restriction on the type of the function gx. Okay, let us test our understanding whether we know when to use the superposition approach and when to use the variation of parameters. Okay, let's look at this equation. X squared y double prime plus xy prime plus 3y equals to 2x. Can we use the superposition approach to solve this non-homogeneous equation? The answer is no, because the coefficients of this equation are not constants. The coefficient of y prime is a variable expressed in terms of x, and the coefficient of y double prime is also a variable expressed in terms of x. Okay, so since there are variable coefficients in this equation, then we cannot use the superposition approach. What about this equation? Can we use the superposition approach? Notice that the coefficients are all constants. However, the gx is a logarithmic function. Since this is a logarithmic function, it does not belong to those group of functions which I have mentioned just now. Therefore, we cannot use the superposition approach to solve this non-homogeneous equation. What about this equation? Y double prime minus 2y prime plus y equals x e to the x. Can we use the superposition approach? Yes, we can use the superposition approach because the coefficients are all constants. At the same time, the gx is a product of a linear function and an exponential function. So the two criteria to apply the superposition approach has been met, and therefore we can solve it using that method. Now, whenever we can solve an equation using the superposition approach, it means that we can also solve it by using the variation of parameters. Okay, because we know that there's no restriction on the application of variation of parameters, there's no restriction in terms of the coefficients, and also there's no restriction in terms of the function g of x. Let us learn how to solve an equation by using the method of variation of parameters. We shall focus on a second order non-homogeneous linear differential equation. Look at equation number 1. It is given by a2 of x y double prime plus a1 of x y prime plus a0 of x y equals to gx. The coefficients a0, a1 and a2 are all expressed in terms of x, meaning that they may be constants and they may also be variables. Okay, to solve this non-homogeneous differential equation, of course we shall start by finding the YC, where we need to form the associated homogeneous equation, replace the gx by 0, and from there we form the corresponding auxiliary equation and find the two solutions y1 and y2, and after that we form the complementary function yc which is expressed in the form of c1y1 plus c2y2. Okay, now we're going to find the yp. We are going to learn how to use this variation of parameters to find the yp. So these are the steps that you need to go through, that you need to follow in order to apply the method of variation of parameters. First step is to evaluate f of x. What is the formula for the f of x? F of x is equals to g of x divided by a2 of x. Do you know where is the g, where is the a2 of x in the equation? The g of x will of course be the function written on this right side of the equation. And when we say a2 of x, it is referred to the coefficient of y double prime. Okay, so a2 of x is this part here. So when you evaluate fx, you take g of x divided by the coefficient of y double prime. So that's the formula for the fx. This is step A. Step B. Evaluate the Wronskian of y1 and y2. What are these y1 and y2? These two functions, y1 and y2, are those that we have found in the yc. Okay, so w of y1 and y2, the Wronskian is given by this. Alright, so you set up a determinant matrix of size 2 by 2. The entries in the first row will consist of the functions y1 and y2, whereas the entries in the second row will contain the first derivative of each of the functions in the first row. So if this is y1, this will be y1 prime, and if this is y2, this will be y2 prime. After that, you evaluate the Wronskian by using the formula A times D minus B times C. That will be y1, y2 prime, okay, minus y2, y1 prime. Okay, so that will be the formula for the Wronskian for the two functions y1 and y2. So take note, if your y1 and y2 in the yc is wrong, so the rest of your work will certainly be wrong. So make sure you get correct functions in the yc. y1 and y2 must be correct. Step C is to evaluate w1 of the two functions y1 and y2. Now what does this number 1 denote? This number 1 denotes that you have to alter the column number 1 in W. In W, the column number 1 is y1, y1 prime. Now you have to replace it by 0 fx. Okay, now what is this fx? You get it from step A. Okay, so whatever value that you got over here, you put it into this part of W1. So only column number 1 changed into 0 fx, but column number 2 of W remains the same. If this is y2, y2 prime, this also will be y2, y2 prime. Once this setup has been completed, you evaluate W1, follow the formula A times D minus B times C. So A times D will be 0 minus y2 fx. So that's why you get the answer as negative y2 fx. Step D is to evaluate W2 of the two functions y1 and y2. W2 means you will have to alter column number 2 of W. So column number 2 of W, you replace it by 0 fx. Again, the fx is the one that you have got in step A. So replace column number 2 by 0 fx, but column number 1 of W will remain the same. If this is y1, y1 prime, then in W2, column number 1 will also be y1, y1 prime. After you have completed the setup of W2, then you evaluate the Wronskian. Use the formula A times D minus B times C. So y1 multiplied by fx minus 0, and that is why we get the answer here as y1 fx. Alright, so those are the steps of evaluating the Wronskians W, W1 and W2. Step E is to evaluate U1 prime. Now, what's the formula for U1 prime? It is W1 over W. So, whatever answer that we got here, right, negative y2 fx, you need to divide it by the answer that you have obtained in part B, W. So, negative y2 fx divided by W. And you also have to evaluate U2 prime. The formula is W2 over W. Right, so W2 is y1 fx divided by W, which you got it from step B. Okay, so notice that to get U1 prime, you only require these three values. You require y2, fx, and W. Y2 has already been determined in the YC. Fx has already been obtained in part A, whereas W has already been obtained in part B. In other words, it is not necessary actually to evaluate part C and part D. You don't have to evaluate W1 and W2 at all. You can skip part C. That means you don't have to apply this formula at all, because U1 prime can just be equal to negative y2 fx over w. You already got y2 in the yc, fx you got it in part A, and w you got it in part B. Similarly for u2 prime, w2 over w, is it necessary to evaluate w2? No, actually. You can skip part D. Right? That means you don't have to evaluate this at all, because you've already known y1 from your yc, you've already known fx from part A, and you have already known W from part B. So my advice is for you to skip part C and D and straight away use these formulas to find U1 prime and this formula to find U2 prime. Part F is to evaluate U1 and U2. Now to get U1, you just have to integrate U1 prime with respect to x. And to get U2, you just have to integrate U2 prime with respect to x. And lastly, we form the particular solution which has this formula. Yp is U1 Y1, okay, U1. Whatever you got over here, you must multiply with the first function Y1 in the YC plus U2. Okay, this is what you got in part F, U2. And then you multiply by Y2, the second function that you've obtained in YC. So this is the formula for Yp when you apply the method of variation of parameters. Next step is to form the general solution. So general solution, as you all know from the previous chapter, for the non-homogeneous differential equation, the general solution is expressed as a sum of Yc and Yp. So y equals to Yc plus Yp. We are going to look at just one example to explain to you how to apply this method of variation of parameters. I only show you one example because we will have more examples of variation of parameters in the following chapter. Okay, the question is find the general solution of y double prime plus y equals to tangent x. Now, can we use the superposition approach to solve this equation? The answer is no, because the gx is a tangent function, and therefore we cannot use the superposition approach. Hence, we are going to apply the method of variation of parameters. To begin, we are going to find the yc, the complementary function. So as usual, we're going to replace the right hand side, the gx, by 0. So here we are forming the associated homogeneous equation y double prime plus y equal to 0. Let us form the auxiliary equation m squared plus 1 equals to 0. So this is a second degree auxiliary equation. We must get two roots. So shift positive 1 to the other side. So get m squared equals to negative 1. And from there we get the root m, which is equals to plus or minus square root of negative 1. But we already know that negative square root of negative 1 is defined as I. So we get two roots, m1 and m2, plus or minus I. So m1 is positive I and m2 is negative I. So m1 is a complex root, m2 is its conjugate. So notice that the real part of m1 is 0 and the beta is equals to 1. So y1 will be e to the 0x cos beta x. So y1 is cos x and y2 will be just sin x. So yc will be c1y1 plus c2y2 or c1 cos x plus c2 sin x. So that is the formation of the complementary function, or in other words, the general solution for the associated homogeneous equation. Alright, now let us solve and find the yp. Okay, I should have written here find yp. Sorry, I missed that. Okay, next step, find yp. So to get the yp, we are going to start by evaluating the fx. Now, what's the formula for the fx? Do you remember? Fx is g of x divided by a2 of x. G of x is tangent x divided by a2 of x. a2 of x is the coefficient of y double prime, and in this case the coefficient is the number 1. So tangent x divided by 1 is just tangent x. Okay, next step is to evaluate w. W of the two functions that you have found in the yc. So y1, y2. y1 is cos x and y2 is sin x. Remember, if you get these two wrong, everything else will be wrong. So be careful, make sure you get these two answers correct. Alright, so your y1 is cos x, y2 is sin x, and the second row will of course be the derivative of each of the function in the first row. So differentiate cos x, you get negative sin x, differentiate sin x is cos x. Evaluate the Wronskian using the formula a times d minus b times c. So cos x times cos x will give us cos square x minus the product of these two will get negative sin square x. Negative negative is plus. So we get a sum of cos square x and sin square x. By its trigonometric identity, this is just equals to 1. So w is just equals to 1. Now we jump into finding u1 prime. We are not going to find w1 and w2 as I've explained before. Okay, so u1 prime has the formula negative y2 fx over w. Now y2 is sin x. Alright. Now you have to follow what you have written here. Let's say you call this as your y1 and this is your y2. Then your y2 must be cos x. So you have to follow what you have written here. In this case, I've labeled y1 as cos x, y2 as sin x, so I must follow what I've written here. So the y2 must have to be sin x. So negative sin x, and the fx is tangent x divided by w, which is 1. Simplify whenever possible. Okay, now sin x multiplied by tangent is sin over cos. Now we cannot cancel anything here, but we know that sine multiplied by sine is sine square x divided by cos x. u2 prime, the formula is y1 fx over w. Now y1 in my work is cos x, so I have to follow what I've written here. y1 is cos x multiplied by fx, which is tangent x, divided by w, which is 1. But tangent x is sine over cos, and fortunately here we can cancel the cosine function, and so the answer is just sine x. So these are the answers for u1 prime and u2 prime. Now I'm going to evaluate u1, where I need to integrate u1 prime with respect to x. Okay, I need to integrate this part here with respect to x. So what do? I'm going to substitute this expression here into this integrand. So I'm going to write down sine squared x over cos x dx. Now you have to figure out how to evaluate this integral. To evaluate this integral, the thing that we can do is to use trigonometric identity for sine squared x, which we know is equivalent to 1 minus cos squared x. So 1 minus cos squared x divided by cos x can be simplified by taking the first term divided by the denominator minus second term divided by the same denominator. Now if you take 1 over cos x is defined as secant x, whereas minus cos squared x divided by cos x can be simplified as just cos x. Now we can evaluate the integral of this. You can refer to the table of integrals to get the integration of secant x and also the integration of cos x. Now we still have to keep the negative sign outside of the integrand, so the negative sign is still there. Now integration of secant x with respect to x given by the table of formula is ln of secant x plus tangent x. And integration of negative cos x is the same as negative sin x. So this is the answer for the integration of this function. Now when you open up the bracket, you take negative multiplied by the ln function, negative multiplied by the negative sin x. So this is what we've obtained, negative ln of secant x plus tangent x plus sin x. Okay, so this is the expression for the u1. U2, sorry, this should be this is u1 again. Okay, so u2 is integration of y1 fx over w with respect to x. Okay, now u2 is given by sin x, and you integrate with respect to x, and the answer is very simple, which is just negative cos x. Next step is to form the particular solution yp. Yp is u1 y1 plus u2 y2. Now u1 is given by negative ln secant x plus tangent x plus sin x. Okay, so this is it. Multiply by y1. Now y1 is cos x plus u2. Okay, u2 is negative cos x multiplied by y2, which is sin x. Okay, so this is the formation of the particular solution u1 y1 plus u2 y2, and the next step is to simplify whenever possible. Right, so if I open up the bracket, I get negative ln secant x plus tangent x multiplied by cos x, which is this part here. Okay, so I bring the cos x to the front of the logarithmic function. Okay, the product of these two is actually this one, plus sin x cos x minus sin x cos x, so this term cancelled. Right, so this will be the final part of the particular solution for the non-homogeneous linear differential equation. And now we can write the general solution y equals to yc plus yp. Okay, yc is c1 cos x plus c2 sin x, and yp will be this part here, negative cos x ln secant x plus tangent x. So that will be the general solution for the given differential equation. Okay, so please study all the techniques that I've already explained to you, because we're going to use the method of variation of parameters again in the following chapter. Okay, so thank you very much.